In this video, I show you how to go about solving related rate problems. To ease you into the idea, suppose you have a side of a square that's growing at a constant rate of 1 inch per second. I'd like to know, is the area growing at a constant rate? Now, in order to investigate this, let's let 1 second pass. When that happens, the side of the square is now 1 inch, and the area of the square is now 1 squared inch, as you can see here in my picture. But if another second passes, the side grows to 2 inches, while the area grows to 4 squared inches. That's a change of 1 inch for the side and a change of 3 squared inches for the area. Now, if the rate of change of each of these is constant, then you should see that the side will grow constantly 1, 2, 3, 4, and so on, while the area will grow constantly and the rate will be 3 squared inches. So the area will then be 1, 4, 7, and so on. But if we let another second pass so that the side now is 3 inches, the area then would be 9 squared inches, and the overall change in the area now is 5 squared inches, not 3. And if we allow another second to pass, then the side of the square would now be 4 inches, and the area would be 16 squared inches, which corresponds to a growth of 7 squared inches from the previous second. So it appears that the rate of change of the side certainly is constant, but the rate of change of the area does not seem to be constant. In fact, the rate of change appears to be actually growing. Notice, though, as time passes, this demonstration is using an average rate of change in order to compare the change of the area and the change of the side. So what we want to do, though, is compare the instantaneous rate of change of the side with the area. Let's investigate the same process using instantaneous rate of change instead. Now, there's an overall process that we use in order to solve a rate of change problem. And instead of giving you the steps and then giving you an example, I'll just work in the steps here as I go through the process. And then I'll just come back and give you the steps in general. These are very general steps. So the first thing would be is, let's try to draw a picture that represents a typical instance of the phenomena that's changing in time. In this case, we have a square. In my picture, I'm going to assume that the side of the square is growing. Think of it as the lower left-hand corner is never changing, and the square is growing to your right and up. Next, let's define some variables to represent the quantities that are changing. We'll say S and A represent the length and the side of the square at just some particular moment in time. Also, we'll now express the known and desired rates of change in terms of derivatives. Now, S and A both are changing in time. So there is a rate of change of S in time. We were told that the side is growing at a rate of 1 inch per second. Notice that ds dt, think of them as like separate quantities. ds, think of it like a change in s, and dt a change in time. And that gives you a good hint as how you match up what derivative symbol with which rates. Now we're interested in knowing what would be the rate of change of the area in time, and is that a constant thing? So next, let's find an equation that relates the variables that we found in these rates. Now, you're often not going to have t in the equation, as it's something that's hard to relate with the variables you have, but you can obviously relate the area of a square with its side. That's just that the area is equal to the side squared. Next, these are both functions of time. I just don't know what those functions are. So I can then differentiate each side with respect to t, doing that derivative implicitly. That will then give me an equation that relates the rates, which is why this is called a related rate problem. So I differentiate each side in terms of time, doing our derivatives like we always do. We get that. That then is our relationship between the rate of change of the area and the rate of change of the side. Now we use the information we know about this particular moment in order to answer the question. I wanted to know something about the rate of change of the area. I know the rate of change of the side. I'll just replace it. So the rate of change of the area will then just be 2 times s times 1, because ds dt is 1, But that would then mean that the rate of change of the area is 2 times s, and s is not constant, remember? S is changing, it's growing. So the rate of change of the area is not constant. It's actually, in fact, it seems to be about 2 times the length of the side that you start with. Let's compare our result against the exploratory data that we've gotten. So here is the exact same square I had moments ago, and I've given you the different values of the side at different seconds and the corresponding areas. Notice at this side length, for this change in the side length, that's the DSDT, we got this average rate of change of the area in time. But the average rate of change of the area in time, that's the change in the area over the change in time, that's approximating. It approximates the instantaneous rate of change, being the derivative of a in terms of t. But we already know that's equal to 2 times s times the change in the side in time. So the average rate of change of the area in time should be approximated by 2 times the starting side, which was 2, times the rate of change of the length of the side. So 5 should be approximately equal to 2 times 2 times 1, which is right. So this seems pretty good. Now, the approximation, of course, gets better if we just use smaller time periods, because I keep letting 1 second pass in this entire process in order to get our average rate of changes of our sides and our areas. If we use a much, much smaller change in time, you would find that the average rate of change is very, very, very close to 2 times the side times the change in the side per time. So let's go ahead and talk about the overall strategy. In order to solve a related rate problem, typically they talk about problems that are changing in time, and they usually refer to changing quantities or something you can notice in some way or represent. So if you can, draw a picture. When you do so, though, represent a common instance, not an extreme case. So your picture should be generic enough to represent all the different possibilities. Second, define your variables and any kind of constants. And when you do so, if you can, reasonably, put those variables or constants in your picture. It'll help you visualize the overall process. Third thing would be to express any rates as derivatives. Usually you're given one rate somewhere. It's usually units of this per that. And there's another rate that you're trying to find. Next, write down one or more equations that relate the variables that you find in your rates, or just the variables that you're using. Try to, if possible, to get one equation that relates the 2 variables that are in the rates that you have. Once you have that, then just differentiate each side in terms of time or in terms of whatever variable needs to be the derivative with respect to. Finally, use the known quantities to answer your question. Let's use this process on another example. Suppose you have an oil tanker that strikes an underground reef and runs aground. The tanker is going to lose 100 cubic meters of oil per hour, which forms a circular-like spill around the tanker. Assuming the oil spill is uniformly about 1 centimeter thick, which is probably not reasonable, how fast is the radius changing when the radius is 100 meters? So first, here's a generic picture. I'm going to pretend the oil tanker is not in the water at all, so we can just ignore that piece. Notice I'm including a little radius to help us visualize things, but I'm not putting in the radius into the picture itself. I'm not putting in an r, the variable, in it, because it doesn't really matter. But I will define the variables that V, A, and R are going to be the oil spill's volume, cross-sectional area, and radius. When you define these variables, it's often a good idea to also include the units you're going to be using. Next, the rates. Well, I know that the oil tanker is losing cubic meters of oil, but that means the oil spill is gaining that volume in time. So the change of the volume of the oil spill in time would be a positive, because it's increasing, of 100 cubic meters per hour. I want to know what's the rate of change of the radius in time. So I need to know dr dt, but given a certain moment, that's when the radius is 100 meters. So some equations. The volume of this oil slick is like a cylinder. It has a constant height. Notice though that I gave you the height of this cylinder as 1 centimeter. I need everything in meters. So 1 centimeter is 1/100th of a meter. So the volume of this cylinder-like surface of oil slick would be 1/100 times the cross-sectional area, which is A. The A, though, represents the area of a circle, so the area is pi times r squared. By using those two equations, I can then write down a single equation that represents the volume with the radius of that particular cross-sectional circle. Now that I have that equation, I'll differentiate each side in terms of time, because volume, that volume of oil, is changing in time, and the radius is also obviously changing in time. So doing that differentiation, doing it implicitly, will give us this. So the rate of change of the volume in time is equal to pi over 50 times the radius times the rate of change of the radius in time. Now at this one moment, I know what the radius is, and I know the rate of change of the volume in time. So I'll now answer the question by replacing my quantities with what I know them to be, and then I'll solve for the rate that I don't know yet. So I know that dV dt is 100, I know r is 100, and then just by solving for dr dt, I would get 50 over pi, and that'd have to be in meters per hour, because r is measured in meters and t is measured in hours. So then that means that this radius is growing at a rate of 50 meters divided by pi per hour. Let's do another example, but this time let's get away from just lengths and involve other more interesting things, like angles. Let's suppose a rocket launches from level ground at 15 feet per second with a flight path that's perpendicular to that ground, and is watched by a camera that's at ground level. Now the camera is going to be 50 feet away from the rocket's launch. I want to know at what rate is the angle of elevation to the rocket changing from that camera when the rocket is 100 feet up. So like last time, here's a very generic looking picture of a rocket taking off from the ground. Notice I made the ground flat, level, and I made the camera just be a little dot. Now let's define theta and h to be the angle of elevation to the rocket, and that'd be in radians per second, and the height, and that'd be in feet, of the rocket. Also, because this time it makes it easier to see, I'm going to put those variables into the picture. The rates that I have, well, I know that the rocket was traveling at a speed, a velocity, of 15 feet per second. H is a position function. It measures the distance from ground to the rocket. So we know the rate of change of position with regards to time, that's velocity. So dh dt, the velocity, is 15 feet per second. Notice the units. See, it's 15 feet per second. See, it's dh, feet, over dt, seconds. The notation makes it a little bit easier to match the rates with the correct derivatives. Now I want to know the rate of change of the angle of elevation. So that would be the change of the angle in time. That's radians per second in our case. So that must be d theta dt. And that's at a moment when the height is 100 meters. Well, we need some equation then that relates the angle with the height. Well, looking at my picture, you can see I have embedded inside of it a right triangle where we have an angle, we have an opposite side h, and an adjacent side 50. So using trigonometry, the tangent of theta is h over 50. I don't feel compelled to solve for theta or to solve for h. You don't need to do either in this case. That equation is just fine. It describes a function of t on each side of that equality. Next, we'll differentiate. So I differentiate in terms of time because that's what my derivatives are in. When you do so, I would then get the secant squared of theta times d theta dt using your chain rule, and that's equal to the derivative of h over 50. Don't write it that way. Write it as the constant 1 over 50 times h, because then you don't need the quotient rule, and the derivative is just 1 over 50 times dh dt. That's an equation that relates our rates. Now I'll answer the question. I'll just plug in what I know. So I know that dh dt is 15, so I can plug that in right away into my equation. But if I were to do that, notice though that I'm trying to find the rate of change of the angle when the height is 100, but there's no height in the problem. There's no h. Oh, but there is a theta. See, the theta, not the d theta, the theta is the angle at that moment of time. So I need to know what the angle is. Well, actually, I don't need to know the angle. All I need to know is what's the secant squared of that angle when the height is 100 meters. So let's look at that one moment. Here's a triangle. This time I have the height being a fixed value. I just don't know what theta is. Well, by using the Pythagorean theorem, you can see that the hypotenuse is 50 times the square root of 5. And then remembering that the secant happens to be the hypotenuse divided by the adjacent side, you get that the secant of theta is the square root of 5. So if I know what the secant of theta is, I know what the secant squared of theta is. Or replacing that then, the secant squared of theta is 5, then I have my d theta dt, and that's equal to 1 over 50 times dh dt, which is 15. Just solving for d theta dt gives me that the rate of change of the angle in time is 3 over 50 radians per second. That's 0.06 radians per second. That's rotating really slowly, which that makes sense because it's 100 feet up. If you're looking at something that's 100 feet up and going up at 15 feet per second, your head's not going to rotate very much, is it? It's going to rotate, but not very much at all. So this seems reasonable. Let's do it one last time. Let's suppose that we have coughing is dripping from a right circular cylinder at a rate of 0.6 cubic inches per second. The coffee will fall into a beaker roughly the shape of a right circular cone. The beaker point up is 8 inches tall with a 10-inch diameter. Now I want to know how fast is the coffee level rising in the beaker when the coffee is 4 inches deep. So here is a typical example of how the liquid could be dripping into our beaker. We have above the cylinder and below the right circular cone. The cone has a height of 8 inches and a diameter of 10 inches. Now, let's see. We know that the volume of liquid is increasing in time at a rate of 0.6 cubic inches per second. So I'll need variables v and h. V for the volume of liquid. I'll need h for the depth, because they mentioned that we have a change in volume and they want to talk about the change of the depth. So I need those two variables at least. But I also noticed that in order to find the volume of the liquid, I'm going to have to do the difference of two volumes of cones. And to find the volume of a cone, I need a radius. So I have the radius of the bottom circle, but I don't have the radius of the cross-sectional area of that layer of coffee. In the problem, they mention a change of volume of the amount of coffee in this beaker. So I certainly need a variable for volume of that liquid. And also, we want to know about how fast that depth changes, so I need a variable for that too. But I'll also need a variable that will represent that radius of the cross-section of coffee that's actually a depth of 8 from the ground, or at least the bottom of the beaker. Because in order to find the volume of that liquid, I'm not to find the difference of two volumes of cones. And to find the volume of a cone, you need both the height of the cone and the radius. So that radius, r, will be changing in time, because as the depth increases, that cross-sectional area, which is a circle, that area gets smaller, which means the radius gets smaller also. Now, for our rates, we have a change in volume in time. That is 0.6 cubic inches per second. And I put down a positive number because the rate is increasing. We have an increasing volume of liquid of water in that beaker. I want to know the rate of change of the depth. So that would be the derivative of h in terms of t, because h is the depth, the rate of change of it then is its derivative. But we want to do that at a particular depth, which in this case is 4 inches deep. Now for some equations, to find the volume of the liquid in the beaker, I'm going to find the difference of two volumes, the large cone and the small cone. Remember, this is the formula to find the volume of a cone. It's 1/3 the height times the base, which is pi r squared. So it's pi over 3 r squared h. So the volume of the big cone, since the height is h and the radius is 5, would be that. And the area of the small cone, well, the height would be 8 minus h. The radius is the unknown r. So we get that for that volume. So we just make the formula look a little nicer, multiplying things out. You would get this. Notice I took out the common factor of pi over 3, and I went and multiplied the 5 squared and the 8. This is our formula. It's at least one equation, though. It's not the equation we're going to use in the end, because we want a formula that has v and h only. Now notice, though, that as h changes, that the r will change with it, and certainly the h will completely determine what the radius would be. So we should expect there's a ratio or some kind of correspondence between the two. Well, but the two cones are similar figures, so the ratio of corresponding parts must be equal. So the ratio of the radii, the radius of the little circle, compared to the radius of the big circle, the two bases radii, that ratio must be equal to the ratio of the heights of these cones. The little cone height is 8 minus h, and the height of the big cone is 8. So r over 5 has to equal 8 minus h over 8. Just solve for r, make it look nice. You get r is equal to 5/8 8 minus h. So take our formula that gives us the volume in terms of the height and the radius. So just replace the radius with the expression I gave you in the formula for the volume, and you'd get this. Just cleaning it up, making it look nice. So then the volume of coffee is then related to the depth of the coffee by this formula. So continuing on, we'll then take that equation and differentiate it in terms of time, doing the derivative implicitly, because the volume and the depth were both functions of time. So there's doing the derivative on both sides, and here I am simplifying the entire thing. If you then go and simplify that expression a little bit further, this is the equation that relates the rates. The rate of change of the volume in time and the rate of change of the depth in time. At the moment of time we're interested in, the depth is 4. I'll just replace the h with 4, and we know the change in volume of time is 0.6. So we get this particular formula. This, if you then solve for dH/dt, gives you that the rate of change of the depth is equal to 6 divided by 625 times pi inches per second, which is not very fast, which is kind of what you expect. You shouldn't expect that as the levels going up very quickly. With the naked eye, you probably wouldn't see it at this point. You wouldn't see their change in the depth at all if you stare at it. Of course, if you do it over a period of time, you would. And that's it. Now, that gives you a basic introduction to how to go about modeling rates of change problems and getting an answer. They are not easy problems. It requires usually quite a lot of knowledge from your previous math classes, your pre-calc, your trig, your algebra, and so on, in order to get the relationship between the variables in the first place. The differentiation is easy, usually, and writing down the rates is usually fairly easy. It's always getting that one equation that relates the variables before you get the rates that's challenging. Just don't get discouraged. If you're not sure, try exploring the idea with some numbers and look at the process in terms of average rate of change instead, much like I did with the very first problem with the square. In any case, good luck.